Alright, this is lecture 7, which is about the CHSH game. So last time we were studying partial measurements of spatially separated qubits, and we saw that at first it seemed like it could lead to some situations that were spooky. And then I tried to convince you that they weren't so spooky after all. Well, actually in this lecture we're going to study this CHSH game, which is a physical experiment you can actually do using these ideas. And it's actually pretty wild and wacky, so maybe it is spooky after all. In fact, you can interpret this game that I'll talk about as proving that the laws of nature cannot be described by any theory of local hidden variables. So we'll find out what that means over the course of the lecture. Okay, so let's discuss what we were talking about last time. So let's say Alice and Bob are each going to own one qubit. Let's call it a photon. And let's say they initialize them both to state 0. And then they bring them together into the same room for a play date, and they run them through this little quantum circuit that we talked about last time. Then what they get at the end of it, this Hadamard and CNOT gate, is the famous EPR pair, the Einstein-Podolsky-Rosen pair, which is two entangled qubits in the joint state 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1. Now, as we emphasized last time, these are actual physical photons, and Alice can put one photon in her pocket, and Bob one photon in his pocket, and hypothetically now they can fly off to distant planets. Alice can fly off to Mars, Bob can fly off to Jupiter, and they each have their photon, but these photons remain entangled, even though they're super far apart. Now, recall what we were mentioning last time. If Alice were to put her qubit into a standard measuring device, the 0-1 measuring device, then her readout will be 0 or 1 with 50% chance each. And supposing she reads a 0 when she puts her qubit into the measuring device, then her state collapses to 0, but also we know that Bob's state instantaneously collapses to 0. And so Alice at this point knows for sure that if Bob were to measure his qubit with a standard measuring device, he would for sure get 0. And on the other hand, if Alice's measuring device happened to read out 1, then Bob's state collapses to the state 1, and Alice would know that Bob would get a 1 if he were to measure his qubit. Okay, so that was not terribly weird, but even weirder was when we noticed that this EPR pair state, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1, was actually equal exactly to the state 1 over root 2 plus 1 over root 2 minus minus. And there I'm referring to the tensor product of the plus state with itself and the tensor product of the minus state with itself. And as we saw in the previous lecture, what that means is if Alice were to put her qubit through a measuring device that measured in the plus or minus basis, then she would again get the two possible outcomes, plus or minus with equal probability. And if her measuring device read out plus, then not only would her state collapse to plus, but so would Bob's state. And on the other hand, again, if her state, her qubit when put into the measuring device in the plus or minus basis read out minus, then she would know instantaneously that Bob's state was also minus, and that if he were to measure in the plus minus basis, he would for sure get minus. Okay, and this seemed a little bit wild because Alice can of course choose which of the two measurement bases to use, and therefore, of her own volition, she can create a situation where either Bob gets the state 0 or the state 1 with 50% chance each, or Alice can make it so that he gets the state plus or minus with 50% chance each. So that looked wild, but as argued in class and is also on the homework, despite these situations looking very different, Bob actually cannot tell the difference at all between a 50-50 chance of 0 or 1 and a 50-50 chance of plus or minus. And because of this, Alice actually cannot use her ability to choose measuring device to instantaneously convey any information to Bob. Okay, so that's what we talked about last time. And now I'd like to show you how Alice and Bob can use this ability to perform what I'll call a magic trick, some kind of interesting magic trick. Okay, so they'll do what we said. They'll prepare an EPR pair on Earth, and then they'll take their qubits very far apart, one to Mars and one to Jupiter. And in this magic trick, Alice is going to measure in one of two bases. Basically, she's either going to measure in the 0-1 basis or the plus or minus basis, like we talked about. And Bob is also going to consider measuring one of two bases. He'll have two different measuring devices. But two bases we haven't talked about before. So one is going to be a pi over 8 rotated basis, and one is going to be a minus pi over 8 rotated basis. That's in radians when I say pi over 8. We can also call it 22.5 degrees. Well, a picture is going to be worth 1,000 words here, so let me draw the picture. Okay, so the unit circle here on the left, next to Alice, depicts the two different measurement bases that she may use, and naturally we'll call them the red basis, which is just the 0-1 basis, and the yellow basis, which is basically the plus or minus basis. Usually with the minus base, you draw it out here. This is the actual vector minus. We've drawn it as negative minus, but it's the same thing. I just wanted to have it rotated 45 degrees. Okay, and normally, let's say with the red basis, we call its two outcomes 0 and 1. And with the yellow basis, we would call its two outcomes plus and negative minus. But as in the picture, I'm just going to call them solid and dotted. Okay, so the red 0 vector, I'll call solid, and the red 1 vector I'll call dotted, and similarly for the two yellow vectors. These two yellow outcomes I'll also call solid and dotted. Okay, this is just because this is how I can easily depict it on the screen. Okay, so you should imagine that Alice has two measuring devices in her hand, the red measuring device and the yellow measuring device, and each of them has a readout, and the readouts say either solid or dotted. Okay, and just as depicted, let me emphasize that the angle between Alice's two, well, the solid vectors in Alice's two measuring devices is 45 degrees. Okay, so what's going on with Bob over on Jupiter? So he's also got these two measurement devices, which naturally we call the orange measuring device and the green measuring device. And again, we're going to imagine that their readouts display the words either solid or dotted, as corresponding to the picture. Okay, and as depicted in the picture, I really mean that the angle here, let's say between Bob's orange solid vector and the horizontal axis, is 22.5 degrees. Okay, that's half of 45 degrees, or a quarter of 90 degrees. And similarly, the angle that the green solid vector makes with the vertical axis is also 22.5 degrees. Okay. So actually, let me show you how these four measurement devices arrows or bases overlap. Okay, so this is what you get if you put them all together. And the top right quadrant here of the circle is exactly split up evenly into four pieces. So these four solid vectors, red, orange, yellow, green, are at successive angles of 90 over 4 degrees. Okay, so 22.5 degrees. Okay, and the main thing I want you to notice in this picture is that the red vector is close to the orange vector. Okay, they're at 22.5 degrees. And the orange vector is close to the yellow vector. And the yellow vector, here I mean the solid vectors in the upper right quadrant, the yellow solid vector is close to the green vector. But the green vector is far from the red vector. So they're at 90 degrees minus 22.5 degrees. Okay, or if you think of these, solid dotted vectors, these bases for measurement as, like a pair like this, then the red one is similar to the orange one is similar to the yellow one is similar to the green one, but the green one and the red ones are quite far apart. Okay, so it's just like in the rainbow. Okay, so let's put them back next to Alice and Bob. And this situation implies, as we'll see more carefully soon, that if Alice were to measure with her red device and Bob were to measure with his orange device, then because these two bases, orange and red, are similar, they actually have a fairly high chance of getting the same outcome, meaning either they both see the readout solid or they both see the readout dotted. Okay? And similarly, if they use orange and yellow, Bob orange and Alice yellow, And similarly, if they use yellow and green. And conversely, if they use red and green, then they have a high chance of getting opposite outcomes. Okay, so this can be summarized with this bipartite graph. Okay, so in the bottom here, orange is sort of similar to, red is sort of similar to orange. Orange is similar to yellow. Yellow is similar to green, but red and green are dissimilar. And let's label them as I have with, the words same and opposite, even though these bases are not exactly the same or exactly the opposite. And for Alice and Bob's magic trick, they're basically going to claim that they're trying to do exactly what's shown on the bipartite graph. Okay, it's not exactly clear what I mean yet, so I'm going to add more detail in a second, but Bob and Alice, for their magic trick, are going to be outputting either solid or dotted, and they're going to be trying to achieve either the same outcome or the opposite outcome in accordance with the bipartite graph there at the bottom. Okay, so it's still maybe not quite clear what I mean, so let me say some more. Now, as in many magic tricks, the two magicians here, Alice and Bob, are going to call for volunteers from the audience, if you will. And it's traditional to call the volunteers, we're going to need two of them, the referees. Okay? So Alice and Bob are actually going to each bring one neutral referee to their respective planets. There's Alice, there's Bob's. And they're going to get right up, in Alice's face on, Alice's referee is going to get up in her face on Mars. Bob's referee is going to get right up next to him on Jupiter. And here's what the referees are going to be instructed to do. Okay, so the magic trick works like this. Alice's referee is supposed to flip a fair coin, just get a regular coin out of his pocket, flip it, and based on the outcome, he's going to issue Alice a challenge. And that challenge will be either red, let's say if he gets heads, or yellow, let's say if he gets tails. Okay, so he gets out his coin, he flips it, and it comes down heads or tails. And based on whether it comes out heads or tails, he exclaims to Alice, red, or perhaps yellow. Okay, and once Alice hears the challenge, she's supposed to immediately, or like extremely soon, ASAP, issue a response, which just means either the phrase solid or dotted. Okay, so in this little example, after the referee said red, just in 1 second, Alice came back and said dotted. Okay, and similarly over on Jupiter, Bob's referee is going to flip a fair coin, okay, to determine whether he'll issue the challenge green or orange. Okay, so he flips his coin, and then it comes up one way or the other, and let's say he says orange. Okay, and then again, like very promptly, Bob has to respond with either the phrase solid or dotted. Okay, and so that's what's going to happen on each of Mars and Jupiter. Looks a little funny, but this is how the game works, the magic trick works. And I actually want to specify a few more things. So I want these two challenge responses to happen at basically the same time. Okay, so let's say the referees, synchronize their watches when they're still on Earth. And, they both agree, okay, they're going to issue their challenge and flip the coin at the stroke of midnight Pittsburgh time, okay? And so they'll, do it more or less at the same time. And then they're going to demand that Alice and Bob respond quite promptly, let's say within 10 seconds. Now, why am I saying all this stuff about time? Well, the reason is we want to make sure that Bob and Alice are acting completely independently. And in fact, see, Mars is like 30 light minutes, 30 to 60 light minutes, I think, away from Jupiter, okay? So if Alice and Bob, are required to respond by midnight plus 10 seconds, there's a window of, 10 seconds during which, they're supposed to give their responses to their challenge. Okay, but light takes, 30 minutes to get between Mars and Jupiter, then that means there's absolutely no way that they could be, like, secretly communicating. Even if they have some cell phones that are hidden from the referees, I mean, it would take 30 minutes for any kind of communication to happen between Alice and Bob, but, the referees are going to ensure that they act within, 10 seconds of each other. Okay, so actually, the referees could even give them up to 30 minutes to respond, but they're not going to need it. Let's just say they respond in 10 seconds. At the very end of this lecture, I'm going to talk about real-life versions of this magic trick. And in one version, Alice and Bob might be like 1 kilometer apart. We're actually not going to put them on Mars and Jupiter. And they'll be required to answer in 1 microsecond, the referee's challenges. Okay, again, too far apart to allow them to communicate within the span of the magic trick. Okay. So the magic trick's not over. Once, the referees issue their challenges and get their responses, then the two referees rendezvous back on Earth, and Alice and Bob can come too if they like. Their role is over at this point. And the referees exchange notes. They might say that, the first one says, oh, I challenged Alice with red, and she said dotted. The second referee in our example said, oh, I challenged Bob with orange, and he said dotted. Okay, and then they look down at the bipartite graph at the bottom here, and see what, Alice and Bob claimed they were trying to do. And in this case, since the challenges were red and orange, that means they were trying to give the same response. And, well, in fact, good, they did. Alice said dotted and Bob said dotted. So what we say is, wow, their magic trick succeeded. Okay? And you can imagine performing, Alice and Bob performing this magic trick several times. They prepare like a new EPR pair, and then they go back to Mars and Jupiter, and the referees go back to Mars and Jupiter and flip their coins and issue their challenges. Alice and Bob give the responses, they go back to Earth, they check the bipartite graph and see whether or not Alice and Bob succeeded. Okay, so Alice and Bob are like a magic team here, and they want to answer the responses in a way that maximizes the probability that their trick will succeed, that their responses will do what the bipartite graph says they're supposed to do. Okay, so let's talk strategy. So I didn't actually expressly say what Alice and Bob do, but hopefully it'll be obvious based on our earlier discussion. So remember, Alice and Bob prepared these personal photons in a bell pair that they brought to their respective planets. And remember also that they have each of them has 2 measurement devices. Alice has a red measurement device and a yellow measurement device. Bob has the green measurement device and the orange measurement device. So they do the thing that you would guess that the whole magic trick is design based around. They're allowed to respond however they want, but the point is, Alice will measure her photon in the basis that matches the color that she's challenged with, and she'll respond with the outcome, solid or dotted, that her measurement device reads out. And similarly for Bob, he measures his photon in the basis colored according to his challenge, and responds with his measurement device's outcome. Great, so let's now try to analyze the probability with which their magic trick succeeds. And the whole point of designing these 4 bases where red was close to orange and orange was close to yellow and yellow is close to green, but green is far from red, is that it's set up so that they'll succeed with high probability. So let's exactly work that out. Good, so here's the analysis. Now, we don't actually know necessarily whether Alice's measures first or Bob measures first, or they measure at exactly the same time. They're going to measure very close in time to each other because the referees demand it. But the good news is, as we saw in the last lecture, it doesn't matter for analysis purposes or for results purposes in what order they matter. Okay, these measurements, partial measurements on a 2-qubit state, they commute in time. Okay, you'll get the same results if Alice goes first, or if Bob goes first, or if they jointly measure. Okay, and so we can choose whatever we want, and let's just assume for analysis' sake that Alice measures her qubit first. Okay, so Alice may be measuring in either the red basis, the 0 or 1 basis, the standard basis, or she might be measuring in the yellow basis, which is like the plus or minus basis. Okay, and this is exactly the 2 situations that we talked about at the end of the last lecture. And as we saw in the last lecture and reviewed at the beginning of this lecture, in either case, if she's using red or yellow, she's going to report or see the outcome solid versus dotted with 50% probability each. But the key thing is, whichever one she happens to see, be it solid or dotted, Bob's qubit state will snap or collapse to exactly the state that Alice's qubit does, and that corresponds to the outcome that Alice measured. Okay, so for example, and this is clearest, in the 0-1 basis. If Alice measures in the red basis, the standard 0-1 basis, and she sees the outcome dotted, which corresponds to the vertical 1-ket vector, then Bob's state will immediately become the vertical 1-ket vector. Okay, and at that point we can determine what would happen when he measures either in the green basis or in the orange basis. And also, as we saw, though, this is equally true if she measures in the plus or minus basis, the yellow basis. So, if she measures in the yellow basis and her readout is solid, then that means that this solid yellow vector is the state that her qubit snaps to, and it's also the state to which Bob's qubit snaps to. Okay, so Bob's qubit always snaps to exactly the vector outcome that Alice's snaps to. Okay. So now, in fact, as I said, let's say that Alice measures in the red basis and she gets the outcome dotted. Okay, so she's going to respond to dotted, and Bob's qubit state will become this vertical vector that we normally call ket 1. And now, let's say that Bob was issued the challenge green, so he's measuring in the green basis. Well, if Alice has this vertical, if Bob's state is now this vertical red vector and he measures in the green basis, then he's much more likely to see the outcome solid than he is to see the outcome dotted. Because the angle between his state, which is now the vertical vector, and the solid vector is 22.5 degrees. Okay, so it's quite close. And therefore it's quite likely that Bob will output green, and that's exactly what he's trying to do. Sorry, that he'll output solid, and that's what he's trying to do. Output the opposite of Alice's output, dotted. Okay, and you can see that in every case, the situation is that the desired measurement outcome for Bob is quite likely because the associated vector will be at exactly 22.5 degrees in every case from his true vector. So just to do another example, let's say Alice again measures a challenge to measure in the red basis, and she measures and sees solid, so she sees the solid red vector, so she responds to the challenge with solid. Her qubit snaps to the state, this red horizontal vector. Bob's qubit also snaps to this red horizontal vector. And let's say he's issued the challenge orange, okay? Then what he's hoping, well, overall what they're hoping to happen is that they'll output the same thing, because we're doing red and orange here. And indeed, since Bob's state is this horizontal vector, it's quite close to the orange vector. It's at angle 22.5 degrees from the solid orange vector. We know that the probability of outputting that good vector for Bob is always the square of the cosine of the angle. Okay, so in every case, the Bob state gets into a vector which is 22.5 degrees away from the one that he really wants it to be in order for him to win. And so the probability that he succeeds is always cosine of 22.5 degrees, well, that they jointly succeed, I should say, is cosine squared of 22.5 degrees. Okay, and that's a number that's quite close to 1. I mean, there's some trigonometric identity showing that it's exactly equal to 1/2 plus 1/2 times 1 over square root 2, which is about 85%. Okay, so this happens in all 4 cases based on the 4 possibility things that Alice and Bob are challenged with. And so we can conclude that with shared entanglement, if they're given each have 1/2 of an EPR pair in this quantum entangled state, then without any communication, they can succeed at the magic trick with probability 85%. And I should say that through the rest of this lecture, I'm just going to keep saying 85%, even though technically it's 1/2 plus 1 over 2 square root 2. Great. So that's the magic trick. It's, normally you want magic tricks that always work. This one only works with probability 85%. So we kind of have to ask ourselves, well, is that impressive? And the thing that we're really asking ourselves is, did they really need quantum entanglement to do this? Is this demonstrating some phenomenon that can only be possible due to quantum mechanics? That's the real point of this magic trick, as we'll discuss towards the end of the lecture. Well, let's try to answer this question. Do they really need quantum to succeed with this rather high probability of 85%? Well, let me start by saying that, the prohibition on Alice and Bob from communicating obviously makes a very big difference in this experiment. I mean, you have to have that. I mean, if Alice and Bob could, secretly talk, or not secretly talk, anyway, if they could communicate at all, then they could share their challenge, the knowledge of what their challenges are. Alice could simply communicate to Bob, oh, say, Bob, I was asked red. What were you asked? And Bob would say, oh, I was asked orange. And then, of course, they can respond to the referees perfectly because they know exactly which, edge they're being tested on, and they can just coordinate the responses. Okay? But that's the whole reason why, Alice goes to Mars and Bob goes to Jupiter, so that they're definitely cannot communicate. Okay? So if they, respond promptly to the referees, then they're so far apart in space that there's no time for light even to travel between them, so everybody can agree that there's no way they could have communicated. Okay, so this spatial separation really enforces that they can't communicate, and that's important because, if they had cell phones, they could just call each other or text each other, then Alice and Bob could succeed with probably 100%, which is much better than their wonderful 85%. Okay, so let's assume that they're not able to communicate. That's crucial. But let's get back to this question of whether it's truly important that they use the quantum entanglement. Maybe they could have succeeded this well without quantum entanglement. So let's start off by first asking ourselves, what if, everything was super classical, like super classical physics, and Alice and Bob were just completely deterministic? Okay, let's model, first of all, as a warm-up, what happens if Alice and Bob are completely deterministic agents. Okay, in that case, when Alice and Bob's referees ask them a challenge, red or yellow or green or orange, if Alice and Bob are deterministic, then, you simply model them as some function that maps their challenge, the referee's challenge, deterministically to a response. Okay, so a deterministic Alice simply looks like, a mapping from the two challenges for her, red and yellow, to either solid or dotted. Okay, and Bob just deterministically, when he gets green, he gives a certain answer, either solid or dotted, and when he gets orange, he gives a certain answer, either solid or dotted. And just before continuing, it's getting too annoying for me to keep saying solid or dotted, and it's also a little bit untraditional. So henceforth, I'm going to call the responses not solid or dotted, but 0 or 1. Okay, so I'm going to change my mind, and now Alice and Bob are always going to respond to the referees with 0 or 1. Okay, but they're still trying to, do the things shown in this bipartite graph. You can either give the same answer or the opposite answer. Okay, so it was time to make that notational switch, so I did. But let's get back to where we were. So if we're imagining Alice and Bob to be deterministic agents, then, right, Alice, when challenged with red, simply gives a fixed value, either 0 or 1. Same for if she's giving yellow, same for when Bob is giving green, or when Bob is given orange. So what's really going on here is just they're giving a labeling of 0 or 1 to the 4 vertices of this bipartite graph. Okay, so if, Alice says 0 when she gets red, and maybe Bob says 0 when he gets orange, and Alice says 0 when she gets yellow, and maybe Bob says 1 when he gets green. Okay? So if that's, how Alice and Bob decide to deterministically play, then what will happen? Well, in this picture, 3 out of the 4 times, based on the 4 possibilities for what the referees can jointly challenge, 3 out of 4 times they'll get the right answer. So they get the right answer when the referee on Alice's side says red, and Bob's referee says orange. They get the right answer, or they succeed when the challenge is yellow and orange. They get the wrong answer when the challenge is yellow and green, because they're supposed to say the same thing there, but Alice says 0 and Bob says 1. And they succeed when the challenge is red on Alice's side and green on Bob's side, because they're trying to say opposite things, and they do. So now you can kind of see it's quite easy to analyze, what is the best success probability that deterministic Alice and Bob can achieve. You just have to think about all possible ways to label the 4 vertices of this bipartite graph with 0s and 1s and trying to match the edge labels. And you can clearly see that, the best they can do is get 3 out of the 4 edges right. It's quite clear. I mean, if red has to match orange, and orange has to match yellow, and yellow has to match green, then red would have to match green, but you also want red to be opposite to green. So, you have to break this cycle in one place, at least, with your labels. Okay, so I think it's very clear that with the deterministic, responses, for at most 3 out of the 4 overall possible pairs of challenges, can Alice and Bob succeed? Okay, so since the referees are picking their challenges randomly, they choose each of the 4 edges equally likely. The best success probability with which deterministic Alice and Bob can succeed is 3/4, or 75%. Okay, you see that's less than the 85% that they could succeed with quantum entanglement, so that's kind of interesting. Well, as always when comparing quantum-enabled parties, we usually think it's unfair to insist that they be deterministic. I mean, that's not very fair. I mean, quantum is inherently randomized, and in normal life, we don't get too worried about people using randomness. That seems fine. So it's much more fair if we allow Alice and Bob to themselves be randomized agents, okay, when attempting to perform their magic trick without quantum. Okay, so we're not going to let them use quantum. Maybe we're skeptical of quantum, but the possibility that they're using quantum, but they could certainly be using their own random coins. Okay, so let's model them as using randomness, and let's model them for now as using what we'll call private randomness, which just means that Alice has got her own coin flips that she's going to do on Mars. Bob has his own coin flips that he's going to do on Jupiter. So more precisely, let's say that after the referees issue their challenge, that Alice and Bob can each flip as many fair random coins as they want in aid of them deciding what their responses will be. Okay, so, because they flip these coins separately to themselves on their planets, we call it private randomness. Okay, so let's just see the picture of how it works. Again, the referee flips his coin and says either red or yellow. Let's say he says red. But now, Alice, in the 10 seconds that she's allotted, well, first she flips, a few coins, perhaps. She flips a couple coins, and based on both her challenge, which was red in this case, and maybe how the coins turned out, she'll make a response, which now, remember, we're just going to call 0 or 1. So perhaps she responds with 1. Again, similarly, Bob making his decision, he gets a challenge, which is green or orange. He can flip some coins and, use both the coin flips and, the name of his challenge to decide what his response will be, either 0 or 1. Okay, so in this scenario, you see that Alice's response is both a function of her challenged color, red or yellow, and also of her coin flips. We can imagine she uses however many she wants. And similarly for Bob. Now we can ask, okay, now with this ability to flip coins, how well can they succeed at the magic trick? And it's not very hard to show. You can think about it as I'm speaking here, that this doesn't really help Bob and Alice. Their best success probability remains 75%. And actually, instead of directly showing you why that's true, what I'm going to do is be even more easy on Alice and Bob, give them even more potential power, and show that with even this more latitude, they still cannot succeed with probability more than 75%. Okay? And what is this additional latitude that I'm going to allow them? Well, I'm going to allow them what we call shared randomness, as opposed to private randomness. Okay, so this is still like a classical setup with no quantum entanglements or anything, but it's sort of even more fair to Alice and Bob because it even more fairly mimics what they do with their EPR strategy, but in a classical way. Okay, remember that, with their 85% strategy, they're sharing quantum entanglement, which they pre-prepared on Earth. And so the most fair comparison, classically, is to allow Alice and Bob to prepare some shared randomness. Okay, so what we're going to assume here is that before Alice and Bob go to Jupiter, they get together on Earth and jointly flip some coins, okay? And, based on the coins they flip, they're going to, record how the coins came out and take this shared random information to their future planets. And so say, I don't know, they chose to flip 4 coins, they could actually flip tons and tons of coins, hundreds of coins, thousands of coins, but let's just say they flip 4 coins, they come up maybe heads, heads, tails, heads. There's no problem with them both making a copy of this random string, putting it in their pockets, just like they put their photons in their pockets when they're using shared entanglement, and then flying back off to Mars and Jupiter. Okay, so now Alice and Bob are sharing some random strings. They're heavily correlated random strings. They're, in fact, identical random bits. And so now the responses can be a function not just of their challenge color, let's say red and yellow in Alice's case, but also of their joint coin flips, this heads, heads, tails, heads that they're both holding on to. Okay, and I want to emphasize, maybe it's not completely clear, but I should emphasize that this setup where they have these shared random coins is strictly more powerful, or it's at least as powerful as the case where they have private randomness. Okay, because suppose Alice wanted to also have some, coin flips that she used to help make her decision that were not, going to help factor into Bob's decision. Well, that's fine. I mean, remember Alice and Bob are working on as a team. So, when they're back on Earth, they can flip a bunch of coins that, like, they plan to use jointly, that they plan to share, like the heads, heads, tails, heads here. And they can also flip, pre-flip their own private coins because, the coins are independent of the referee's challenges, so they can pre-flip their own private coins. And Alice can even, see Bob's private coins and take them and copy over with her to Mars and not use them. And similarly, Bob, it's okay if he sees Alice's private coins and takes them with him to Jupiter. They're working as a team. They're not obligated to use all of the coins that they share. Right. So they just the shared randomness only helps them. They make a big batch of random coins. They copy them down. They go to Mars and Jupiter. They feel free to factor them into their decision however they want. Okay, well, what I want to claim to you is even still in this most liberal model where they're allowed to share randomness, they still can't succeed with probabilities better than 75% of the magic trick. Why is that? Well, it's actually very simple. So, well, let's just imagine what happens in this particular case that I've illustrated here on the screen where they happen to flip the joint random coins heads, heads, tails, heads. Well, in that case, given these coin flips, heads, heads, tails, heads, Alice's, remaining strategy, condition on these coin flips, is just some deterministic function of the challenge she receives, either red or yellow. Okay, and similarly for Bob. So once you fix the outcomes for their shared random strings, then the remaining actions are just a deterministic function of their color challenge. Okay, so again, conditioned on the shared randomness, they're really just giving a 0-1 labeling to the graph. And we know that in this case, they succeed with probability at most 75%. They can be getting at most 3 of the 4 edges correct. Okay, so the conditional success probability, conditioned on their shared randomness being heads, heads, tails, heads, is at most 75%. And a similar thing will be true no matter what their shared coin flips are. Suppose they flip 4 coins and they happen to be tails, 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 tails. Well, condition on that outcome for their shared coins, the remaining deterministic function of the color challenges might be a different labeling of the 4-vertex graph. But nevertheless, it can still only get 3 out of the 4 edges correctly. So if they flip tails, 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 they get almost 75%. Conditionally, if they flip tails, 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 heads, their conditional success probability is still at most 75%, because at best it's just some other labeling of the vertices of this bipartite graph that can get at most 3 edges right. For any outcome of their coins, the conditional success probability is at most 75%. So, no matter what the coins are, they get at most 75%. So overall, their success probability, even when you factor in the randomness of their shared coins and the randomness of the referee's challenge, its overall success probability is at most 75%. Okay, so even in sort of this most liberal classical model for allowing randomness in everything, Alice and Bob cannot perform this magic trick with success better than 75%. Whereas, just to remind you one more time, by sharing one EPR pair, 1 qubit each in a 2-qubit entangled state, this state here. Let me get to the right slide. Right. When they share this bell pair state, 1 over root 2, 0, 0 plus 1 over root 2, 1, 1, they have this strategy with the overlapping measurement bases that succeeds with probability at least 85%. So let me summarize all that we've seen so far about the best success probability that Alice and Bob can achieve for this magic trick. Okay, well, actually, let me first tell you the real name of this magic trick. I mean, it's not called the magic trick. This is called the CHSH experiment, or the CHSH game. And I'll say a little bit more about its history in just a few moments. In any case, we saw that if Alice and Bob behave deterministically, they can succeed with at most 75% chance. If they have private randomness, they get at most 75% chance success. If they have shared randomness, they get at most 75% success. But if they can share quantum entanglement, they can succeed with probability at least 85%. Okay? And on one hand, 75% versus 85%, these numbers are not too different, but I mean, the amazing thing is that they are different. I mean, 85% is strictly better than 75%, so it shows a real quantum advantage, something they can do quantum that they cannot do at all, even with quite a liberal notion of probabilistic behavior. Let me just briefly mention a couple of things. First of all, I actually showed you that that there was some strategy that Alice and Bob could use with measuring entangled quantum states that let them succeed with probability 85%. Turns out that's actually the best that they can do for this peculiar CHSH experiment, this bipartite graph-based experiment. This was shown by Sorelson in 1980 that no matter how many qubits they are allowed to share and how they can measure, the best thing that they can do with it is 85%. Okay, great. So 85% is what they can do. Let me also mention that why is it called the CHSH experiment? Well, it's named after four scientists whose surnames start with CHSH. This is Clauser-Horne-Shimony-Holt. This is from 1969. What CHSH did in 1969 was actually just a relatively minor variant of a similar experiment that was proposed by John Bell in 1964. And Bell was the one who really came up with the idea of having an experiment that would, in this way, drastically and dramatically highlight the difference between what you could do with shared classical randomness versus shared quantum entanglement. Okay, and so actually it's funny, the main thing attached to Bell's name these days is Bell's inequality. But Bell's inequality is actually the quite pedestrian fact that with shared randomness they can do at best 75%, which is kind of like the easy part of the argument, the completely elementary analysis. So he got his name attached to the simple half of this argument. But actually, maybe the nice thing you can attach his name to is the phrase Bell inequality violation. That's pretty cool, right? So you can say that when, if you're allowed quantum entanglement, then you can succeed in the CHSH experiment, probably 85%, and the fact that 85% is greater than 75% is called a Bell inequality violation. But, it can really happen according to the laws of quantum mechanics. Right, so I actually want to focus on a little bit describing this distinction between shared randomness and shared quantum entanglement. And I should add that in the quantum mechanics literature terminology, this concept of shared randomness is usually called the local hidden variables model, or sometimes the local realism model. So what does it mean, the local hidden variables model? Well, it's kind of baked into the name. So actually, if you recall last lecture when we were discussing what you could do with an EPR pair, and we said that once Alice measures in the 0-1 basis, she instantly knows that Bob would get what he would get if he measured in the 0-1 basis. This is sort of the spooky action at a distance thing that the eponyms of the EPR pair, Einstein, Podolsky, and Rosen, were quite unnerved by. But then, that in itself didn't seem too crazy once we reminded ourselves of a classical analogy. So we said, imagine that on Earth, Alice and Bob program a computer to pick a random bit, either 0 or 1, and then the computer prints out the 2 copies of that bit in 2 sealed envelopes. Alice and Bob don't see it yet, but Alice and Bob each take one of these sealed envelopes containing the same shared random bit to their respective distant planets. And then if Alice, quote unquote, measures her bit just by opening the envelope and looking at the contents, whatever she sees, let's say 0, she instantly knows that Bob's envelope also contains a 0, and that if he were to open it, he'll also measure 0. And similarly, if she opens her envelope and sees a 1, she instantly knows that Bob has a 1, and that he would measure 1 when he opens his envelope. So this is just the shared randomness scenario. There's some shared, some random quantity, which is shared by Alice and Bob, and it's sort of stored locally in the envelopes, okay? So the real state of the contents of the envelopes exists. This real state already has been decided on. It's either 0 or 1. We don't know what it is, but, as the analyzers of this scenario. But each bit in these envelopes has a real state, and it's stored locally in the envelope. Okay, so this kind of explanation is, or this kind of model is called local realism. And Einstein hoped to find some variant or some addition to the theory of quantum mechanics in which all the experimental results could be explained by local hidden variables. So it requires, every measurement result could be explained by some, local state that each particle had that determined fully the measurement outcomes, which is actually not what happens with, EPR pairs and this measurement strategy that we saw that lets them win with 85%, Alice and Bob. So, just to be clear, there was a hope, among Einstein and others, that everything could be explained by a local hidden variable scenario. So the hope was that, let's say, when Alice and Bob were, preparing their photons and getting them together and passing them through this Hadamard gate and C0 gate, that somehow this entangling operation, was the time when, Alice and Bob's qubits somehow jointly decided how they would respond to all future measurements. Somehow they would go through and, say, okay, if I get measured, I'm speaking for Alice's photon here. If I get measured in the 0-1 basis, I'll say 1, and if you get measured in the 0-1 basis, you'll say 0, and somehow they make some joint decisions here, and these joint decisions are stored locally somehow in the state of the particles. And then when these particles are moved super far apart, all the necessary information is there in the particle to explain all future measurement outcomes. Okay, so if quantum mechanics were like this, then it would, be in this local hidden variable scenario where, or this shared randomness scenario where all the information necessary to explain the results of experiments is, stored locally and can be explained in this model that's like the model of shared randomness. But as we saw, as we argued, that if quantum mechanics really were explainable by local hidden variable theories, then it would be impossible to have success in the CHSH experiment with probability more than 75%. But according to the non-local rules of quantum mechanics that, well, existed before and after Einstein's time, and which I've told you over the course of these lectures, seemingly there is a way that you can succeed in the CHSH experiment with probability greater than 75%, namely 85%. So we have a very tense situation here where any believer in local hidden variables would not believe it's possible to achieve a success rate of 85%. So, well, now we ask, can the CHSH experiment be done in practice in the real world? Can we actually, entangle an EPR pair and move the qubits far apart and, flip the coins for the referees, make an experiment that does this, measure them appropriately, and then check for success? If we can set this all up and then, do it 1,000 times and then count the number of successes, well, if we get, some number of successes that's like 850 or even a number of successes that's like a lot more than 750, that proves that, there's no local hidden variable theory that can explain the state of these two photons. Well, it turns out that the answer is yes. So there was actually some limited experiments to, do the CHSH and Bell type experiments in the 70s, but the first really good ones were done by Alain Aspect and colleagues in the early 1980s. That's a picture of him. It's a figure from one of his 1982 papers that shows the setup of the experiment. And so they did the experiment. The entangled particles were measured when they were like 13 meters apart from each other, which is, I guess, 40 light nanoseconds. But the measurements were, done in 5 nanoseconds, so that kind of had the spatial separation aspect and no communication aspect enforced. And the success rate of the experiment was like 84%. which is quite great. I mean, it's well above 75%, and it was quite close to the 85% predicted by quantum mechanics. And, his experiment was quite, careful, and it eliminated all the loopholes, or most of the loopholes that people thought of that might let you wiggle around the assumption that you were violating a local hidden variables theory. In his paper, he said, the best loophole criticism that he could think of that remained was that his referee coin flips, if you will, were not, completely random. They came from some quasi-periodic oscillation of the measurement devices, and he said, that's pretty random. I mean, I don't think these measuring devices are conspiring with the qubits in any way. So, I mean, people basically agreed that this experiment did it. It proved it. Aspect's actually quite an interesting guy. He got his BA and his master's from I think a less prestigious school in France, and then he went to Cameroon for 3 years to teach. And then he decided to come back to France to get his PhD, and he actually did these experiments confirming the impossibility of local hidden variable theories for quantum mechanics during his PhD thesis. And 20 years later, he got all sorts of physics prizes for his work in this area. So that's great. I mean, it's, quantum mechanics, the laws, this non-local entanglement, the fact that, Alice's measurement affects Bob's future measurements in a certain way, not in a way that allows them to communicate, but in a way that makes their measurement outcomes correlated. It's kind of amazing. And, some people are still not too happy about accepting it, and they would prefer if there was some way to explain it away. But they've done more and more experiments that just confirm that it's true, and they've eliminated every possible loophole you could think of. In fact, 4 years ago at Ronald Hansen's lab in the Delft University of Technology, they did a massive experiment where they crossed every possible T and dotted every possible I, according to what I understand, and closed every possible loophole that people had thought of. They had their silver electrons in microwaves that were at opposite ends of the Delft campus. It was 1,300 meters apart. And they did, I think, 294 repetitions of the experiment, successful repetitions. And actually, the success rate was not 85% or 84%. It was only 80%. But, it's still noticeably bigger than 75%. And the p-value by which they could reject the null hypothesis of shared randomness or local hidden variables theory was 0.039. Okay, so quantum mechanics is totally vindicated, and it seems that you can create this spooky action at a distance, and you can create these highly counterintuitive consequences of quantum mechanics by entangling particles together. And so, now that we're given this and we're fully confident in these laws of quantum mechanics, our next lectures are going to be really about what really cool stuff you can do, given that quantum mechanics allows for these cool effects. So we're going to see pretty soon quantum teleportation and quantum money, and very soon we'll start to talk about quantum computation itself.